The next topic we're going to cover is oscillators. And so oscillators are circuits that are designed to produce a periodic output with no signal input. So of course we're still going to need our power supplies, but we don't have any signal input. And so of course instances where oscillators are very useful are things like timing or clock circuitry. So we're going to look over the course of this unit at two general types of oscillators. So the first type of oscillators that we're going to consider are going to be sinusoidal oscillators. And so of course these are going to produce some sort of clock signal or some sort of oscillating wave that has a sine wave. The second type that we're going to look at is square wave oscillators, and these can also be referred to as two-state because they sort of have two stable states, or relaxation oscillators. And so of course our square wave is going to look something like this. And so as we talk about specific oscillator forms, we're going to talk about how we can control the frequency of the waves. For our square wave, we'll talk about how to control or calculate our duty cycle and various things like that. So recall that in our previous unit we were talking about feedback and stability. And throughout that unit we were talking about systems that had negative feedback. And so this negative feedback, we said, was very useful for several reasons. It extends our bandwidth. It's providing us less sensitivity to individual transistor parameters, various things like that. But with our oscillators, what we're going to see is that we're actually going to be looking at the case when we have positive feedback. And so actually one of the things that we mentioned when we were talking about disadvantages of negative feedback way back at the start of our feedback and stability unit is we said we have this chance to become unstable if certain conditions are true around our feedback loop. And so that's what we're going to see happen here in a second with our simple diagram. One thing to mention too though is when we have this positive feedback, we have the chance to have some nonlinear behavior in our system. So we're going to take that sort of case by case. But basically that ideal model with our simple block diagram is going to break down. So let's start by looking at this simple block diagram for a basic amplifier. So we notice this looks very similar to what we had seen in our feedback and stability unit, with a couple differences that I want to point out. The first being that this network down here for our beta is now frequency dependent. So previously this beta did not depend on frequency. So previously did not depend on frequency, but now we're saying that there is going to be some frequency dependence in this network. And as we look at specific circuits, we're going to see, of course, in some cases that'll be obvious. Maybe we have components such as capacitors in our feedback network, and of course a capacitor will have some frequency dependence. Another thing that I want to point out is we have this Vs over here, and you might be saying, well, didn't you just say that our oscillators aren't going to have any input? And so yes, that's true. In this case, we have included this Vs just to aid our analysis, just to make it a little bit easier to compare to what we talked about in our feedback and stability unit. The same type of thing is going to be true if we didn't have our Vs being input into that summer. Okay, so with that out of the way, let's recall what our ideal closed loop transfer function was. So our closed loop gain, or our gain with feedback, we said is a function of frequency, and so recall our S is just equal to j omega, is equal to the open loop gain of the amplifier, which was a function of frequency, divided by 1 plus A of S times beta, but now we're saying that this beta is also a function of frequency. So we have something that looks like this. So this is our closed loop gain, or our gain with feedback, and this is again for our ideal case. We also had defined an important parameter called the loop gain, which we also said was a function of frequency, T of S. And so that was A of S times beta, and the only difference is now we're going to say that beta is also a function of frequency. So this is our loop gain. So what we had said when we were dealing with feedback and stability is we actually kind of touched on this a little bit when we were talking about our phase margins and our gain margins. We had said that for our feedback and stability, we had said we want to have this T of S greater than 0, so we want it to be positive in order to have our negative feedback. And so we sort of talked about different ways we could design systems, how we could adjust poles in order to keep that system stable. But now with our oscillators, what we're going to say is we actually want to have that loop gain be less than 0. So we're saying we want the TS less than 0, which is of course going to result in positive feedback. And so why positive feedback? Well, so what we can see if we come back up here to this basic block diagram is we can see we have this negative sign at our summer. So we're actually subtracting this value. So if we are subtracting a negative value, we're essentially going to be adding it. And so what that looks like then is that error signal is going to be equal to our input, which in this case was our V of S, plus our VFB, because we are subtracting a negative value. So here we have our positive feedback coming into play. Another thing that we can see is if we look at the specific instance of this loop gain being equal to -1, what we can see is that from this ideal transfer function, that means that our closed loop gain is going to be infinite. So that means our A of S is going to infinity is this, and so instead of equals -1, let me say as this goes to -1. And so, of course, what we can say if we put that in terms of words, that means we're going to have an infinite output, or sorry, not infinite, let's say we're going to have a finite output for 0 input. And so this is kind of one of those weird mathematical things. 0 times infinity, of course, that would be 0, but basically we're saying if it gets even just a little bit above 0, we're going to have this really, really large thing in an actual circuit, because what we can see is we're not actually going to be able to reach this TS equals -1 and still use that ideal model, because as we approach this, we're going to get some of those nonlinear effects that we talked about earlier, which means our ideal model sort of breaks down. So we're not necessarily going to get an infinite gain, of course, but what we're going to see is we can get really large outputs for very small or not 0 inputs, but basically we're always going to have some electrical noise. So this electrical noise in the frequency range that makes our TS approximately equal to -1 is going to be able to create this positive feedback. So I know that's kind of all very confusing. So let's sort of state this a little more clearly and specifically with something called the Barkhausen criteria. Okay, so our Barkhausen criteria. And so there's 2 parts to this, and basically this is condition for oscillation at a certain frequency. So condition for oscillation at a specific frequency, so let's say at a frequency omega naught. And so what it is we say the first part of this condition is that the magnitude of our loop gain function, T of j omega naught, is equal to 1. And the second part deals with our phase, and so we can say that our phase angle of T of j omega naught is equal to n times 360, where n is equal to 0, 1, 2, and so on, so a positive integer. And so what we can see is that we had talked about in our feedback and stability that this occurs when we have a magnitude of 1 and a phase of -180. And so why is that 180 degrees different from this 360 degrees here? And so the answer to that is that this is actually our angle through 3 things. This is our angle through the gain of our amplifier A, our feedback network B, and that negative part of our summing junction. So our summing junction. So if we come back up here to our loop, basically we can see as we're going through this loop here, we're now considering three things. We're considering our open loop gain of the amplifier, our frequency dependent beta, and also this negative sign of our summing junction. So what we can say then is that the total phase shift around our feedback loop should be 0, or some multiple of 360. So total phase shift, and so this is our condition for positive feedback, around our FB, our feedback loop, is 0, then in parentheses, or a multiple of 360. Or we could also say we are implicitly assuming negative feedback, so that this beta sub s is introducing 180-degree phase shift. And so that's sort of a different way that you might see this written, is that the beta s is introducing 180-degree phase shift, and that would be if we're considering that we had a positive feedback implicitly here. Of course, if we think of on our complex plane, if we multiply a value by a -1, we're essentially changing that phase angle by 180 degrees. So that's why that, in addition to the 180 degrees from our beta s, gives us our 0 or multiple of 360 in our Barkhausen criterion. And so one other thing that we can note about this Barkhausen criterion is that this is actually just a special case of our Nyquist stability criterion. So a special case of, I'll just write our Nyquist stability criterion. And so this would be the case, we talked about our Nyquist stability, our Nyquist plots, and we said we can plot this on our complex plane. We have our imaginary and our real axes, and we plot our Nyquist plot. And so maybe it looks something like this. So we had some positive frequency part and some complex conjugate that was a negative frequency part. And what we do is we compare that to our point -1, 0, and we say, does the plot enclose that or go through it? And if it does, then our system is unstable. So in this case, I've drawn this for a stable system. But our Barkhausen criterion is actually the special case where our Nyquist plot goes through that point. So for instance, we could redraw this, and we could put our point right here so that that's going through -1, 0. So this would be our Barkhausen criteria related to our Nyquist plot. So that's all a bit difficult to grab just at first. So what we're going to do is we're going to go through and look at some specific configurations. We're going to switch the order up a little bit compared to how it's presented in the notes, and that's just so that you guys are more prepared for your next lab coming up. But the downside of that is we're going to get away from this sort of basic definition a little bit at first, and then we're going to come back to some circuits that are more related to it a little later on.